All right. Yeah. Okay. Welcome everyone to the ZAG seminar. Today's speaker is Jorgen Rennemo from Oslo. Will tell us about K-theoretic sheaf counting invariants on C4. Yeah, take it away, Jorgen.
I will. Yeah. Right. Yeah. So as you can see on the screen, and as John said, the title is K-theoretic sheaf counting invariants on C4. Well, thanks to thanks for the introduction first of all, and thanks to John and Jorgen, all the organizers, for inviting me to speak. So this is joint work with Martin Kool, and it's about more precisely, it's about a new computation of certain K-theoretic sheaf counting invariants on C4. So, but the main goal is for me to sort of explain. I'll spend much time trying to get to the point where I can explain what these invariants are, since these are relatively new. They're relatively recently defined. And I'll tell you the result we have about computing them, and hopefully the main goal is for this to sort of illustrate what these are in the. So these invariants exist more generally, but in the case of the of C4 is where you have the simplest definition of them, which is rather concrete. So that's what I'm mainly hoping to be able to communicate in this talk. So this is a story where we're doing something in dimension 4, which we, or not we, but which one was previously able to do in dimension 3. So the plan is to start this talk by some extended discussion of the parallel story in dimension 3. So we start by considering C3. So we think of this as affine 3 space, and T, the standard 3-dimensional torus, acts on this. And so in 3 dimensions, the story is Donaldson-Thomas theory. So let me get the pieces on the board to introduce Donaldson-Thomas theory for this variety. So we start by looking at space Hn, which is my notation for Hilbert of C3. So the Hilbert scheme of endpoints, on C3. So this is a modular space, and sort of so the key, technically the key, so geometrically this is a pretty horrible space, for large enough n of unknown dimension, and it has all sorts of terrible singularities. So the reason this is an interesting space to study in the numerative geometry is technically it's the fact that it has a perfect obstruction theory. Which I won't go into specifying what that is, but the thing that's useful to remember, or useful to say about this in this context, is that this is, roughly speaking, like the data of at each point. So it's perfect obstruction theory of rank 0, and that means at each point Z in this Hilbert scheme of endpoints. So here we think of Z as a closed subscheme of C3. So at each point Z in Hn, we have the tangent space of Z, which one can compute to be the first X group of the ideal sheaf of Z, and we have the obstruction space. So these are two vector spaces. So the obstruction space set, which one can compute, well, rather this is perhaps more of a definition, but appropriately defined, turns out to be x2 of IZ. Okay, and we have said reality gives us now that gives us that the dimension of the tangent space here is equal to the dimension of the obstruction space. So that means that the virtual dimension of this virtual dimension of the space Hn is 0. So naively or not so naively, these the tangent space parameterizes like the infinitesimal deformations of set, and then the obstruction space, or rather the dual of the obstruction space, parameterizes somehow the potential set of equations one imposes. So since the set of deformation directions is equal to is the same dimension as the set of equations, one expects the dimension to be 0 in some sense. But all of this can be made precise, and the technical output of having this data is that from this technically via a paper of Berendt and Fantecchi, you can sort of turn a general crank in a machine and produce you produce two things. You produce one thing which is somehow more well, one thing which applies more generally and is more famous of these two things. So the virtual fundamental class here. So some class, roughly speaking, representing, you know, what the fundamental class would be if the equations were transverse, is the general intuition. So that's actually not what we're interested in today. So since we're looking at K-theoretic counting invariants, we're looking at the virtual structure sheaf. So despite the name, I mean, despite the name of virtual structure sheaf, this is actually just the K-theory class. This is just a K-theory class on HN. And it's important that these things are all, since T acts on C3, T also acts on HN, and acts on all the, well, acts on everything in sight, basically. So you get the virtual structure sheaf is in fact an element in the T equivariant K-theory of HN. So now, to define Donaldson-Thomas invariants, so once you have a virtual fundamental class, more generally in an enumerative geometry, you might want to integrate that, take its degree in an appropriate sense to produce invariants. And if you do that to the virtual fundamental class, you get well, at least the most classical notion of Donaldson-Thomas invariants. So the thing we're looking at today is the slightly more refined, or well, it's a different type of invariant, which is the K-theoretic Donaldson-Thomas invariant. So again, I mean, there are various versions of this, but the simplest one you can write down is to say, take this thing, take the Euler characteristic. So if you have a K-theory class, you're allowed to take its Euler characteristic, and you would output an element and you would get an element in the K-theory, T equivariant K-theory of a point, so the representation ring. So that's not quite correct. So I told you a bold lie. Now you're not allowed to do this just a priori. So a key point here is that the space, the Hilbert scheme of endpoints, is non-compact. So if you're trying to define the Euler characteristic just by taking alternating sums of cohomologies, you would get something a priori infinite dimensional and not well defined. So really, rather, what you're doing is you can define this thing via localization. Via localization to the fixed point, to the t fixed points. And this thing is compact. So the consequence of this. So this, I mean, for the purpose of this talk, it's not important exactly what localization is. It's just some procedure which allows you to given a t-equivariant class, given a t-equivariant K-theory class on HN, you turn the crank of localization, and you're able to output some element in this in a variant of this. So some localization of this t-equivariant K-theory of a point. So what is this localization concretely? Well, turns out, well, this the localization of this this K group is the ring of rational functions in T1, T2, and T3, and here the Ti are the parameters of T. Okay, so through a series of black boxes, we're now able to say, given a Hilbert scheme of endpoints on C3, you're able to output a rational function in 3 variables. Okay, so I'll get to so this is all based on like pretty abstract and difficult technical machinery, and we'll get to a point where I can explain to you concretely what these things are in this special case of HN. But before doing that, I want to explain to you how, even without specifying exactly what they are concretely, how they are very much computable concretely. So you can reduce their computation to combinatorics. So we not only have this abstract statement that we can define this thing using localization, but we also have a localization formula. So I told you the fixed point locus here is compact, but I can tell you more about what it looks like. So it consists of isolated points, and the description of it is pretty straightforward. So this thing, so let's just sorry. So HN you can think of as the set of all ideals in this, so ideals in a polynomial ring of 3 variables such that the dimension of the quotient as a C vector space, the dimension here is n. Now the fixed points here, that's the same set, but you force that's the same thing, but you require that I let me write this down. So still the dimension n, but you require that I is a monomial ideal. And so meaning generated by monomials, and then it's easy to give a combinatorial description of the set of monomial ideals, where this is in bijection with the set of plane partitions, which you can picture. I can't draw this, but you can picture this as a stack of n boxes in the corner of a room. So the fixed points are labeled by all the different ways you can stack n boxes in the corner of a room, such that you can't push them further into the corner. That's the simplest way to think of these. Anyway, so we have complete control over, at least we have an explicit way of listing all the fixed points, and then we have the virtual localization formula. So a general statement to Jorgen and Fontanini. Kapranov tells us the following thing: that to evaluate this thing, what you're doing is you're summing over fixed points. So sum over all fixed points, and you do following. So here I use the notation wedge bullet of something is 1 minus the thing plus wedge 2 of the thing, and so on. So the alternating sum of different wedge powers. Okay, so in this case, you get wedge bullet of the dual of x2 iz. Okay, so how do we interpret these things? I mean, these things, I should clarify, I should specify that these things, these sext groups here, so these are T representations. Well, T representations, and that means by taking a trace where will always be in computations identifying them with polynomials in the TI. Okay, so I'm giving you what this recipe tells you, and these xi are then completely explicitly computable for each given set. So for each n, you are given a computable list of fixed points, and at each fixed point there's a contribution which will be a rational function in the TI. And you're summing these rational functions, you get the invariant that you care about. So in some sense, you've removed the geometry from the problem, and it's now well, if you do the computations, it turns into a kind of a combinatorial problem. So just to I kind of want to do the n equals 1 case, just to see what sort of computations go into this. So sorry. So H1, the Hilbert scheme of 1 point is just C3, and the fixed points here, T fixed points, are just the origin is the unique fixed point. And what do these representations look like? the tangent space at the origin is a three-dimensional representation, which we so identifying with its character, we can identify it with this polynomial here. And x2 becomes in the computation, it's the second wedge power of the x1. And plugging this into the formula gives us that the first, so this localization formula gives us the computation of this invariant. The Euler characteristic of the virtual structure sheaf is 1 minus t1, this rational function. Oh, rather, sorry, the other way around. Oh, okay. Huh, like this. Okay. So we have a so at least this is this invariant which we have defined in some mysterious black boxy way is computable. Now to say we understand this, I feel like it'd be good to also give you a straightforward definition of it, and it turns out this straightforward definition of it is also crucial in computing with it. So I want to now give you the simple geometric definition. Or the simple definition, perhaps. So some definition which works in this case, which doesn't work in general. So we have so up to this point we've said HN is something which carries a perfect obstruction theory, and turning the crank you get this K-theory clause. So here's how you can see this K-theory clause explicitly in the case of HN. So the main idea is that HN is a critical locus of some function on a smooth scheme. So the general, this is a sort of a general technical fact about Donaldson-Thomas theory, meaning studying the enumerative geometry of moduli of sheaves on Calabi-Yau threefold. There's a general theorem saying that moduli of sheaves on a Calabi-Yau threefold are locally written as critical loci of a function on the smooth variety. So that's that's a key local fact about these moduli spaces. So the wonderful thing that happens with the Hilbert scheme on C3 is that it's actually there's no need to be local or analytically local or anything like that. It's just globally you can write down a variety, and this Hilbert scheme is a critical locus for a function on this bigger smooth ambient variety. So the way to see this is you think of Hilbert scheme of endpoints on C3. So we previously described this as the modular space of ideals. Alternatively, you can describe it as the modular space of surjections. Surjections onto some n, where the dimension of n is n, and well, this thing is a module over this polynomial ring in 3 variables. Okay, so this you can then consider the following alternative. Well, I'll write it as a set, but it turns out to be a moduli space. You can do the same thing where you take surjections, and now you simply pass from taking the commutative polynomial ring to studying the ring of the non-commutative polynomial ring. And you do the same thing. So as a C vector space, the dimension of this should be n, and well, this thing should have a structure of module over this. Module over this ring of non-commuting, well, polynomials in non-commuting variables xi. So there's so I mean, one has to be slightly careful about how one defines. I mean, when are 2 surjections considered equal? But it's kind of well, I hope it's plausible that if you set this up correctly, there's an inclusion here. So basically, there's the condition for something in here to actually lie in here is that the xi commute when acting on the n. So if you upgrade this to an actual honest moduli space, you get what's called a non-commutative Hilbert scheme of C3. So I don't want to, like, the notation here implies that non-commutative Hilbert scheme is something you can, you know, like that this is some kind of functor or something on varieties, and that's not the case at all. I mean, this is just it's not like I could take the non-commutative Hilbert scheme of some other general variety. It's just a piece of notation saying this is the non-commutative analog of the Hilbert scheme for C3. So the surprising fact about this thing is that this non-commutative Hilbert scheme is a very much nicer space than the Hilbert scheme itself. So the non-commutative Hilbert scheme is smooth and of dimension n plus 2n squared. All of that follows from noticing that there's a GIT description of it. So there's you can describe this by taking this particular vector space and taking GIT quotient by the natural action of. So there's some sentence-ability condition, but it's simple. I mean, once you have that observation, you get the dimension and the non-singularity pretty easily for that. So the Hilbert scheme lies inside this bigger smooth space, and basically now you can have the function. If you now let W be the function on the non-commutative Hilbert scheme, be the function given by W evaluated at a given point. Well, a given point here is a surjection onto some n, and I want to cook up a function out of that. Well, I do this by taking the trace of the following non-commutative polynomial. So here, this is an element in the endomorphisms. I think of this as an element in the endomorphisms of n. So I'm allowed to take the trace of that. It's acting on some vector space. That gives me, so the trace of something is a complex number. So this is a well-defined, at least at level points, is a well-defined function, and you can write down the formulas for it. And the point is now Hn is the critical locus of W, or the vanishing locus. In in a scheme theoretic sense. So this is, I mean, if one wants to understand this, then this is it's a very fun exercise to do to check that this is actually the case, that differentiating W produces all the commutation relations between the xi. So now, I mean, the idea of the virtual structure sheaf is it was supposed to be what. So the virtual structure sheaf is what the structure sheaf would have been if the equations cutting out Hn were transverse. So that means, I mean, this at least makes it plausible, and we can justify it rigorously, that the virtual structure sheaf here, the virtual structure sheaf is given by, so this gives a crucial complex description.
Oh, excuse me?
Yeah.
Where does endomorphism Cn triple come from this W?
Sorry, could you repeat that?
So here you said the Cn plus endomorphism Cn triple 3 quotient by, this is the critical.
Oh, right, yeah, this, oh, yeah, so you're asking
how did it
about,
come from?
where does this come from?
Yeah.
Yeah, so let's see, so how do you specify, the idea is you start by, so the data is, let's call this, let's see, so let's call this, so the idea is you take, so n we know is n dimensional, so we think of this as just Cn a vector space, right? Okay, so we're given a vector v in here, which is okay, so let's call this phi. Then you said phi 1 is v, and then you have endomorphisms here. Let's call these psi 1, psi 2, and psi 3. That's the other piece of data, and then you say that xi, you have to specify this, what am I saying? So these remaining three here encode the module structure of n. So the multiplication by xi, this should be given by specifying that. So this data specifies the module structure on n, and this specifies the map, basically, from the. Yeah.
Then why is the critical point, critical locus?
Sorry, why Hn is the critical locus?
Yeah.
So it's a computation, but if you spell out what it means for this thing to vanish by just writing down, like taking all the partial differentials of this function.
For each value.
Yeah, so the thing that drops out is that all the partial differentials vanish exactly when these things commute.
Okay, thank you.
Yeah. So we've produced Hn is defined by the vanishing of this one form. So you can write down the appropriate Koszul complex, which is now O and C help. Right. The tangent space, NC help, and then wedge 2 of the tangent space of NC help. Okay, so and then this stops at some point. So you write down the appropriate Koszul complex, and this turns out, so you take the class of this, and it turns out that this actually defines for you an element in the K-theory of Hn. So, and not only that, I mean, taking the cohomology of this gives you even a sheaf refinement of the virtual structure sheaf, which you don't have in general. So, okay, so the problem is now, how do you compute this? You have the localization formula, and you have the geometric, description of it as an object defined by a Koszul complex. So I'm not going to. I'm going to say what you compute this to be equal to. Just briefly. So the surprising thing is that it has a nice. It turns out to be surprisingly nice. And there's no way to predict this from the localization formula. You're just getting a sum. The localization formula gives you just a sum, some wild sum over various, over lots of fixed points with various rational function contributions. So it turns out if you post precisely the right problem, you get a nice answer. And precisely the right problem, by this I mean you should not be considering the virtual structure sheaf. Well, you can, but you won't get a nice answer. So instead, you should consider this thing with a hat, which is the symmetrized, what's generally called the symmetrized over. And there's no, I don't want to justify that any more than just saying this is the one that leads to a nice formula. But so you take the virtual structure sheaf and you twist it by some specific line bundle. Okay, then there's just a matter of like some notation which just saves some space. Square brackets just means square root minus inverse square root. So these formulas tend to have lots of these expressions going into them. There's in order to phrase the theorem, one needs the notion of the platistic exponential, which is it has a direct definition by saying given any function, the platistic exponential is defined by this formula. So it's not obvious for any function that this is something well defined or convergent, but I just claim in this theorem it will be. You can think of these as formal power series expanded in a certain way, and it would just works. And more.
Excuse me, very sorry. Now, what is K in the first line?
Sorry, K in the first line here is the canonical model.
Oh,
yeah. Yeah, different from the other K. Yeah. Right, and the way to sort of see this as a kind of natural thing is that if f is the trace of some representation, then platistic exponential corresponds to I should be writing this as a sum instead. So and this is the sum of the traces of all the symmetric powers of V. Okay, so here's the theorem then. If you make sure you treat this symmetrized over instead of the straightforward over, then this has a computation which has a very natural form. It is the platistic exponential of a very simple rational function. So at least like from one perspective, this is saying that there is some. You can think of this as saying there is some more sort of fundamental quantity here, with the exponent from which you get, or from which these Euler characteristic of these symmetrized virtual structure sheaves, the generating function of them is sort of you can extract that from some more fundamental quantity here, which is the exponent. So and this is not at all obvious. But yeah, so this is a very surprisingly nice computation, and this computation breaks completely if you don't symmetrize. So good justification for considering the symmetrized overs. There are other reasons as well. So, you know, we're way past the halfway mark. I can now turn to the story that me and Martijn are telling, which is the 4D story. So now we're looking at C4, and we're looking at the corresponding Hilbert schemes of endpoints, corresponding objects. The parallel objects here are the Hilbert schemes of endpoints on C4, which of course are even worse, have even worse behavior from a geometric perspective. So we still have, so we let T, so the torus in this picture is still the three-dimensional torus. So here you have parameters T1, T2, T3, and T4, and the torus we're acting on by is the one where the product of these is 1. So you impose this condition, which means that this torus you're acting by preserves the volume form in C4. So another way of saying this is C4 is equivariantly Calabi-Yau. So that wasn't necessary. Preserving the volume form wasn't necessary in the 3D case. It turns out to be so. Turns out to be necessary in the 4D case. So if you want to run the same story of producing, say, Donaldson-Thomas invariants, you quickly run into problems of a very simple sort, which is that this thing does not carry perfect obstruction theory. And the reason why, I mean, it's hard to give a reason why something doesn't exist, but it's easy to see that so the dimension of the tangent space minus the dimension of the obstruction space, in this case, that is the dimension of x1 iz minus the dimension of x2 iz. So this would be the virtual dimension if it were to have a perfect obstruction theory. This is not independent of z. Right, or it might be for n equals 1, but that's kind of an accident. So in general, I mean, the thing you would use to build a perfect obstruction theory doesn't necessarily exist, or it just doesn't exist. So there's so it turns out that there is a variation on this idea, which has been worked out. It's been sort of in development for some time, which allows you to still define computable invariants, and the very naive numerological accident that, so from a very naive perspective, the thing that tells you that you might be able to do something is the following strange observation, that this thing, dimension of x1 minus half the dimension of x2. This thing, we can check by said duality, is constant. So previously we had these deformation directions, and we would take these, for the dual space of these equations. Here we're looking for some way to make sense of taking half these taking half of these equations and using that to define a sensible class. So I mean, this seems like a very weak reason to expect that to be a sensible theory, but it's just a stronger piece of evidence is that people have actually constructed the actual theory. So and by people I mean Owen Thomas, so this is last year, they define, so in a general setup, they define over hat in equivariant K-theory, some class in equivariant K-theory for M a moduli space of sheaves on Calabi-Yau threefolds. So for M a moduli space of sheaves on Calabi-Yau fourfolds. So there's previous work here, which, well, related constructions previously by Borisov and Joyce and Cow and Leung, which do similar things in define invariants as homology classes rather than K-theory classes, and they don't have equivariance, and they work with more in differential geometry or derived differential geometry. So the advantage of Owen Thomas is they do this completely within algebraic geometry. And as an upshot, I mean, working within algebraic geometry is generally easier, if you can do that, generally technically easier than doing things in differential geometry. So what they get, well, primarily they get a definition which didn't even exist before, but they also get a localization formula. So they get a which is which looks very much like the one we had before, but it can't be exactly the same because it's not, because we're no longer doing Donaldson-Thompson invariants and perfect obstruction theories. So it looks pretty similar, except for 2 points. So one is they have to symmetrize. So here, by just putting this hat on something, I mean I symmetrize it. So putting a hat on this wedge bullet is the same thing as tensoring with this inverse square root, and moreover you have to take the square root of this thing. Okay, so at a very naive level, formally, this taking the square root of this of the enumerator here corresponds to the fact that you're taking half the equations. You want to take half the equations you had before. So this is again something which is explicitly computable, just as we have in a 3D case. And if you run the explicit computation, you get the following formula. And now, so the formula isn't really computing the thing I wrote down in the localization formula. We're not computing just these bare the Euler characteristic of these bare classes. We have to tensor it by something else, so it's not terribly important. So you're tensoring with here, this thing is the so-called tautological bundle on Mn, and Y is a formal parameter. And yeah, I mean, this is so Y is just a labeling parameter, the same way Q is a generating function labeling parameter, and you end up with then having a very similar formula to what you had in the 3D case. So there's something I want to mention, something which is kind of there's something strange about the chronology here. So this was conjectured by Nekrasov in so 3 or 4 years ago, before we had the definition of these things. So really the precise statement here is one, Nekrasov conjectured. So it was believed. So first of all, Nekrasov works in physics, so he had his own sort of physical interpretation of what should go on the left-hand side of this formula. But it was, but it was also, he also proposed that it would be interpreted along these lines. But it was also a conjecture that these would satisfy this localization formula. So you could formalize a precise conjecture saying the output of that localization formula so the output of the localization formula would produce the right-hand side. So there's one interesting feature of this is if you look at the sort of historical feature of this, if you look at the localization formula here, then this is almost a reduction of the problem to combinatorics. But there is so there's a choice, not a choice, but there's a prescription for which square root to take. So one can, if you look at this formula, I give you a polynomial here, and I give you a polynomial here, and I tell you to take the square root of the top one, then you will always have two choices. You can always change it by a sign. So this sign was well, so in Nekrasov's conjecture, this sign was pretty mysterious. Now that we have the geometric theory, we know we have a geometric prescription for how to define that sign, and computing this, what this sign is one of the major steps in the proof of the theorem we prove. So I wanted to tell you one more thing here. So I've given you a result, and I wanted to give you just one thing which I find pretty neat, which is the fact that in this case, just as in the case of the Hilbert C3, we have there's a completely explicit and concrete description of what we actually are computing in the way that in the 3D case we had this Koszul complex. So it turns out that like this Owen-Thomas invariant is something you can define using very general abstract machinery. But for this case, we actually only need a very simple thing, which is the 4D toy model, which is the following thing. If you let M be a moduli space, well, that you're interested in, and M is a closed subscheme of A, where A is smooth, and you're given the data, of the following thing. So previously in the 3D case, you would say we want M to be cut out. We want M to be defined by the critical locus of a function on A. Here we rather want to be given an SO 2K seed bundle Q on A, so a vector bundle with a quadratic form and an orientation, which is we want to make things as simple as possible, which is split, by which I mean that Q is equal to E, the large sum of E and E dual for EA rank K vector bundle. Okay, and then I want there to exist a section S of Q, so we can write this section. So we can write, instead of writing a section S of Q, we can write the section S So a section of the components of Q, and we put a condition on this, which is that is isotropic with respect to the quadratic form on Q. And finally, the condition is that this section S is what defines M. So M is the vanishing locus. M is cut out by this section. So the general sort of technical heart of Owen Thompson's work is to prove that this, to study this kind of local model and to show that if you have a modular space of sheaves on a Calabi-Yau fourfold, then you can locally describe it in this way. Well, for some appropriate notion of local. So this is the analog of moduli of sheaves on a Calabi-Yau threefold being locally a critical locus. So once you have this this toy model set up, then you can define the class simply and explicitly. Then we can define this class O hat ver by writing down a complex, which is, let's start with the ambient space, and you take a Koszul type thing. So you take, the section of the dual, and this sort of generates for you some. This generates for you a Koszul complex. So you don't quite take that. You also have to throw in some arrows going the other way. So it's section of E. So you have arrows going both ways. What that means is this isn't really a complex in the usual sense. This is really just a Z mod 2 graded complex. That's good enough for K-theory. Okay, so you take this and you have to twist it by some. You have to normalize it somewhat. Anyway, this then gives the definition of O hat ver in the case of a toy model, and then a key observation which makes this, which is, well, both sort of psychologically comforting and also crucial in the actual proof of the formula we prove, is that exactly the same thing, or the analogous thing to what worked in the 3D case actually works in the 4D case. So you can really, this embedding of the Hilbert C4 inside of the smooth thing is an instance of the toy model. So I'm not going to write this down, but they're completely explicit. There's a completely explicit bundle Q which you can write down, which is split, and an isotropic section cutting out Hilbert C4. And from this, you have this this explicit presentation of O hat ver, which is which is technically crucial in order to get the proof of this geometric component of the proof of this off the ground. But I think I'll stop there. So thanks for listening.
Great. Thanks, Jorgen. Are there any questions? So this expression in the generating function, that it looks pretty scary. There's there's some square roots that are involved in the.
Oh yeah, yes. So these square roots I agree they're scary, but they cancel. This product is some polynomial which doesn't have square roots. So remember that this brackets notation here means
yes,
and so writing things out, I think. Or maybe that's not where they cancel out, but they do cancel out. This is a compact way of presenting a given rational function, essentially.
So does that rational function have any sort of meaning?
I suppose not any meaning that's clear to me. But I mean, what one can. No, yeah, not any meaning that's clear to me. What people can say in physics is not it's not for me to say. But what you can also say is somehow, okay, so there's a general, the way the proof goes, which I won't go into, but the way the proof goes makes it clear that the generating function you care about, you should expect this to be the platistic exponential of something nice, where rational function counts as nice. And then you also expect, like, just by considering the situation here, this is all symmetric in the 4 variables. There's no distinguished direction in C4. So the rational function has to be invariant under permutations. And then, yeah, this is almost the simplest kind of rational function you can write down with the symmetry criterion. And I'm not going to claim you couldn't write down the simpler one, but it's close to the optimum in terms of what you could hope for. But yeah, I mean, for me, it's not like I have no reason to, without doing the computation. At some point, one sits down and actually looks at the contributions in the localization formula and see that this is what falls out. So I couldn't have predicted this without computing.
So Necroso just found this from like computing many. I mean, how do you find them? Like,
well, yeah, no, it's definitely a matter of. So there might be some physics intuition, but in 2017, a large part of the evidence for this conjecture was computing up to like n equals 10 or something. And there, I mean, this is an interesting, I think at least an interesting historical sort of fact that part of the evidence was the sign at each fixed point was unknown which sign to take. And what counted as sort of numerical evidence for this conjecture was there was precisely one way to choose the signs so that you got a nice answer, so that this works out, which is, is suggestive. And now we know there is a geometric reason to why there's just one canonical choice of signs. So yeah, it was really based on like a lot of numerical evidence. So it was a pretty safe bet that this conjecture would hold.
Nice. Any other questions? Doesn't seem to be the case. So yeah, thanks again, Jorgen. And yeah, I'll stop the recording here. Yeah, so see you next week. Yeah.